All right, so today we're going to talk about piecewise functions. And piecewise functions are just functions that are in pieces, for lack of a better explanation. So we're going to take different pieces of linear functions and we're going to squish them together. All right, so here's what we need to be able to do by the end of today. We should be able to identify a piecewise function. It's going to be pretty easy because the function is going to look really weird, and so will the graph. We need to be able to evaluate piecewise functions, and we want to be able to do that whether we have a graph or just the function. Evaluate just means what's the value of that function at a particular input. What output goes with a particular input. Domain and range fits into that conversation as well. And of course we want to be able to graph piecewise functions, write functions from graphs in addition to that. Okay? So, all right. Let's take a look at one type of piecewise function, and it's actually a graph that you've created before. Back in Algebra 1, we did these time graphs where we put time on the x-axis and then some measurable variable on the y-axis. And then as time progressed, the graph changed, right? We wanted to increase some places, decrease in other places, and some places we wanted just the graph to stay the same. So let's take a look at a time graph in this situation. So Jimmy and Mary are going to go on a date. Jimmy left his house and drove to pick Mary up at her house. They drove back towards Jimmy's a few blocks to get to the Olive Garden. Always nice breadsticks. They enjoyed a nice 2-hour-long dinner where they chatted and ate and that kind of thing. They then had to, in order to get to the movie theater, drive past Mary's house where they watched the blockbuster, What a Mathematical World. It was, quite honestly, the best hour-and-a-half movie they had ever seen. So Jimmy then took Mary home, and because they enjoyed the movie so much, they talked about it in the car for 30 minutes before Jimmy drove home. All right, so to create the time graph here, remember, think back. Again, the y-axis tells us how far Jimmy is from his house, and the x-axis is time. And since time never stops, the graph is going to keep moving left to right. It's just going to change directions here and there based on the situation. So first, Jimmy's sitting at his house, which means he is 0 miles from his house, which means that we need to be sitting down here at 0, 0 on the graph. Now, he needs to drive to Mary's house to pick her up, and we don't know how far away Mary's house is or how long it's going to take him, so we can kind of do this, whatever. Make it look whatever. So let's say 20 minutes to drive the 6 miles to her house. So since he is leaving his house, the distance that Jimmy is from his house is going to be increasing, so we move the graph up like that. At this point, he gets to Mary's house, and guys, let's be honest, she's not going to be ready. They never are. And so he's going to have to sit there for a few minutes and wait on her. So since he's sitting there, he's not getting any further away or closer to his house, so the graph levels off a little bit. And then he's driving back towards his house to get to the Olive Garden. Of course, he doesn't make it all the way to his house. So maybe about right there. We don't know how far away it is. So in the first hour, so we've already broken up the time into different parts of this first hour, and the graph has changed in those different pieces. Now, for the next 2 hours, they're going to be sitting having dinner. So again, he's not getting any further away or closer to his house because he's just sitting there. And so the graph levels off. Again, another piece. We've broken the x-axis up into a section that went from 1 hour to 3 hours. Now, once dinner is over, they're heading to the theater, which is past Mary's house. Right, so Jimmy's increasing his distance from his house now. And then they sat, I don't know, let's make it like this, and watched an hour-and-a-half long movie. And then once the movie was over, he took Mary back home. So he is still going to get closer to his house, but he's going to stop at Mary's house. So he'll be however far away Mary's house is from his. And then they talked about the movie for 30 minutes, so he's sitting there, he's not moving anywhere, so again the graph is going to level off, he's not getting any further away or closer. and then he goes home. Okay? So this is a piecewise function. This is a piecewise graph, right? Let's see. We are breaking this graph up into different pieces. These are not exactly straight vertical lines, so bear with me. But when we break this graph up into pieces, what we're really doing is breaking the x-axis up into pieces, right? So at one moment the graph is increasing, the next it's not doing anything, increasing or decreasing, and then so you can see all these different pieces. 9 pieces in total. Okay, and those are all different linear functions that are just being cut off. And we're cutting the x-axis up. That's what we're doing. The x-axis is the domain, so we're cutting the domain up. So this is one type of piecewise function. All right? Another type is a graph that we can create, or a function that we would need to model this particular situation, which is the admission rate at an amusement park. And any tiered situation, and what I mean by tiered is, depending on your age, or, depending on one measure, you're jumping up to a different level. Income tax is a tiered system where the more money you make, the higher your percentage is of your tax rate. If you go and mail a package at the post office or UPS or FedEx, you have to pay postage, and it's always based on how much the package weighs. Different weights get you up into a category where you pay a little bit more. So tier situations are going to be this type of function, a piecewise function, but a special piecewise function. All right, so let's get into the graph. So again, on the x-axis, we have age, and on the y-axis, it's admission rate. So depending on a person's age, we want to show what the admission rate would be. Well, first we see that children 5 years old and under get in for free. So obviously you're going to pay $0 for that child. So zero's right here. So even if you take a newborn, which is not even 1 year old yet, to the amusement park, they're not going to have to pay admission for that. Okay? As a matter of fact, they're going to get in for free. Those kids are going to get in for free all the way up until not 5, because even if you're 5 and a half, or 5 years and 11 months, or 5 years and 364 days, they're still going to get in for free. It's when they turn 6 that the rate changes. So we want to go all the way up to 6, but not include 6 in our free group. Okay? Since we don't want to include 6, it kind of goes back to those inequalities that we graphed in Algebra 1 on a number line. If there's a number that we want to show on that graph but not include, we always put an open circle. Right? So that says we're going to go all the way up to 6, but 6-year-olds are not in the free group. Once they get to be 6 years old, they now have to pay $5, or they don't. The parents are going to have to pay $5. So we're going to jump up to $5 for the admission rate when the kid turns 6. And we're going to pay $5 for that kid all the way up until not they turn 12, but they turn 13. And again, at 13, they don't pay $5. So we don't want to include 13 in that group. But we want to go right up to 13. And that open circle shows that. Once they turn 13, they're going to pay $12. So we include 13-year-olds in that $12 group. And you're going to pay $12, excuse me, for that kid all the way up until they turn 19. Okay? At which point 19-year-olds are going to have to pay $18 to get in. They're now adults. And again, we say that because children over 12 years and up to and including 18 years are $12. So we have to go past 18-year-olds and get to the 19-year-olds. Because 18 and 11 months is still going to pay $12. And once you become 19, you're paying the adult price of $18, so that graph continues on. So this is what we call a step function. and because it looks like steps. And like I said, any tiered system, any tiered situation will end up looking like a step function if you try to create a graph to model that situation. And so there we go. The next thing I want to point out to you, we haven't seen yet, is the idea of these open and closed circles. And in a function, we need that. We need for a particular domain value, remember domains are the x values, the range are the y values. For any domain value, you're only allowed to map it to one range value. So for every x, you're only allowed to map it to one y. So if x here is 6, then the graph tells us we have to map it to 5 on the y-axis, not 0, right? We can't have two different values for 6. And so we have to put an open circle in one place of the graph and a closed circle in another part of the graph so that we can have a value for the input of 6, but not have 2. Okay? So on each break in our graph, every cutoff of our graph, we're going to have an open circle and a closed circle. We're going to need to talk a little bit about how to determine that. All right? Those are piecewise functions. They're two specialized types of piecewise functions. And so our definition of a piecewise function is any function represented by a combination of equations, so different equations, each corresponding to a part of the domain. So we talked about breaking the x-axis up in the Jimmy and Mary date situation. And we did the same thing in the amusement park situation too. Age was on the x-axis, and we broke that x-axis up into different groups, age groups. And based on the age group, the price of admission was different, so the graph looked a little bit different. So we're breaking up the domain, and we're having each domain have a different equation that sort of creates the graph for that part. All right? Okay, so we just talked about a step function in the amusement park. Here's what a step function would look like in function notation. Okay? This is your function notation for any piecewise graph out there. Okay? Looks weird. This is function notation, f of x. We place the f of x in an equation in place of y. It's just notation. There's no kind of work that we need to do there. It's just symbols. It's how we write functions. Okay? Then the next thing that you would find in a piecewise function are all the different equations that we have for the different parts of the domain, or the different parts of the x-axis. And then after that, that equation, these inequalities over here to the right, are going to tell you what part of the domain that equation goes with. So for example, the equation, it's f of x equals -1. We can always replace that f of x with a y. Y equals -1. This is an equation that is going to be the graph for this part of the domain, this part of the x-axis. So let's start breaking our x-axis up. So from 0 to 1, so I'm going to draw a dotted line through 1 on the x-axis, so a vertical line. And now from 0 to 1, I'm going to get one part of the graph. Then from 1 to 2 is another part. So I'm going to create another section of the domain by drawing in a vertical line. And then from 2 to 3 is another graph. And so I'm going to draw a vertical line through 3 to break up the domain one more time. So now there's 3 different sections to this particular graph, this function. And since I can interchange f of x and y, I'm going to do this. In each section, I'm going to write, above each section, I'm going to write the equation that we need to be graphing for that particular part. So y equals -1 is going to go here. Y equals -3 is going to go here. And y equals -5 is going to go here. Now all we have to do is graph the line and make sure that we're only showing the part of the graph that needs to fit into that section. So in other words, I'm going to graph y equals -1 first. And maybe the easiest way to do this at first is just go ahead and graph the whole line, and then we'll erase the parts that we don't want. So y equals -1. There's no x, that means there's no slope. These are just linear functions. No slope means we've got a horizontal line through -1. So we draw a line through -1 on the y-axis. But we only want to see the graph in between 0 and 1 on the x-axis. That means I need to erase every other part. I don't need that part, and I don't need this part. I only need the part that exists between 0 and 1 on the x-axis, and so that's that guy. Now, as far as the domain goes, as far as x values go, I want 0 to be part, 0 on the x-axis, that needs to be part of the graph for y equals -1. That's because we want y equals -1 to be the equation that we use when x is 0, because we see in the inequality x is greater than or equal to 0. So we want to include 0 in this part of the graph. So when we do that, we want to put a closed circle when x is, right there where x is 0. And then we see on the other side of that inequality that we do not want to include 1 in the domain for that part of the graph. So when this graph hits 1 on the x-axis, we want to put an open circle to show that we don't want to include 1 there. The inequality, this next inequality says we want to include 1 in the next part of the graph, which is y equals -3. So we're going to graph y equals -3, which is just a horizontal line through -3. And then we're going to erase the part we don't want. And the only place we want this graph to be shown is in between 1 and 2 on the x-axis. So that part right there. And again, because of that inequality, x is greater than or equal to 1, we want 1 to be included in this part of the graph, so we're going to put a closed circle. But we do not want 2 on the x-axis to be part of this graph because that inequality is not equal to. So we put an open circle where x is 2. And then between 2 and 3 on the x-axis, we want to show the graph y equals -5. There's the graph. We only want to use the part of the graph that sits between 2 and 3 on the x-axis. So we're going to erase here and erase here. We look at the inequalities. We look at the inequality here and see that we want 2 on the x-axis to be included in this part of the graph, but we do not want 3 as part of the domain of the graph here. So we open circle where x is 3. And that's your graph, that's your step function. We're stepping down. Okay? And you notice that at every break in the graph, every vertical dotted line, we have an open circle and a closed circle. Right? They're just in 2 different places. So we want to make sure that we have an open and a closed in 2 different places. Okay? All right. Try your hand at a step function yourself. Here's the function. Go through and try to create the graph, and you can stop the video and then start it back up, and I'll talk you through quickly on how to on creating the graph and show you what you should have gotten. Okay? Okay, how'd you do? Well, we take a look at our inequalities first, and that's how we're going to break up the x-axis. We want sections from -10 to -8. So that means at -8, we're going to stop and change the graph. And then from -8 to -6, the graph is going to look even different again. And then from -6 to -4, the graph is going to look different again. So those are all of our breaks. And so now we're just going to graph each line and then erase back to just showing the part that we want to show. So in this section from -10 to -8, we want to graph the line y equals 4. And then again, just replacing the y with the, or replacing the f of x with the y. Then we're going to graph y equals 6 here and y equals 8 here. Y equals 4 and no x, no slope, which means we have a horizontal line, we have a flat line, through 4 on the y-axis, so we graph the line. but we only want that line to exist between -10 and -8 on the x-axis, so we erase the rest of it. We erase this, and that's the part we want. We do not want to include -10 in this part because the inequality is not equal to, so we have an open circle here at -10 on the x-axis. We do want to include -8, so we close circle in -8. And then from -8 to -6, we want the graph y equals 6. So we graph y equals 6, no x, no slope, which means we have a flat line. Horizontal line going through 6 on the y-axis. We only want this graph to exist between -8 and -6 on the x-axis, so we erase back to where we see -8 and -6. We do not want to include -8 in this part of the graph, so we open circle, but we do want to include -6 on the x-axis, so we close circle there. And then the last part, y equals 8. So y equals 8 would be this horizontal line. We only want this line as long as x is between -6 and -4. So we erase this part. We erase this part. We see that we do not want to include -6, but we do want to include -4 on the x-axis, and so a closed circle there. And that's because of those inequalities again. Okay, so that's your step function. All right, hopefully that makes sense. If not, make sure that you get in and get some questions answered as soon as possible. Okay? All right. Now, those are step functions, and sometimes I think step functions are a little bit more difficult to take a look at right away than other types of piecewise functions. So here's a piecewise function that's not going to be a step function, and we can talk about graphing them, and we're going to talk about it the same way we did the step functions. You may find these to be a bit easier. Okay, so here's our piecewise function. We have our function notation. We have two different parts of the graph, which means that your domain is going to be broken up into two parts. There's going to be a less than part and a greater than part. And it breaks there at 2 on the x-axis. So, at 2 on the x-axis, we're going to make a vertical dotted line and know that the graph changes there. Okay? And so we want this equation when x is less than 2. Well, x is less than 2 are all these values back here. So this is going to be the left side of the graph. We want this equation when x is greater than or equal to 2. Well, all the x values that are greater than or equal to 2 are this way. So that equation is going to be what we use for the right side of the graph. So again, replacing the f of x with the y, we're going to graph y equals -2x plus 3 here, and graph y equals x minus 1 here. All right, and so we're just going to graph the lines and erase the parts that we don't want. So -2x plus 3. We go to 3 on the y-axis, that's the y-intercept, and this equation does have an x, so there is a slope. That slope is -2, so from that y-intercept, we're going to go down 2, right 1. I'm not quite to the break in the graph, to the dotted line, so I'm going to go down 2, right 1 again. And then we can graph our line. Okay? But we only want to use this equation when x is less than 2, when we're the left part of that dotted line. So we don't need this part of the line. All right, so we're going to erase back to here, and now we take a look, and our inequality up here says that we do not want to include 2 on the x-axis as part of this graph, so we're going to open circle right here. Okay? Now, we're going to graph y equals x minus 1. X minus 1 minus 1, -1 is the y-intercept, so we put a point at -1. Slope is 1 over 1, so we go up 1, right 1, up 1, right 1, right? And then we can go up 1, right 1 again, and this becomes your graph. Now, we want this equation, we want this line when x is greater than 2. And all of our greater than 2 x's are over here. So we want the right side. So we're going to go through and erase the left side. The inequality that is sitting there for x minus 1 is this guy right here. So that inequality says that we do want to include 2 on the x-axis in this particular part of the graph. So we want a closed circle on that break. And there's your piecewise function. We're just graphing 2 lines, cutting off those lines, and making sure that we use the part of the line that the inequality tells us to use. Okay? That's it. Hopefully that makes enough sense. You got one here to try on your own. Oh, sorry, I almost forgot. No, actually we want to talk about evaluating these functions. Okay? So I'm going to quickly create the graph. Oh, sorry. I'm losing my train of thought here. We want to talk about evaluating. So I want to know what the value of the function is when x is 4. So I want to know what f of 4 is. I want to know what f of negative 1 is. I want to know what f of 2 is. And I want to know what f of negative 50 is. Okay? Now, function notation. That's all we're talking about here. F of 4. What is f of 4? What this notation right here means is that I want to know what the value of the function is when x is 4. Okay? That means 4 is going to be my input. 4 is going to be x. I don't do anything with that. It's not f times 4. I don't get 4f with that. What I want to do instead is I want to go to 4 on the x-axis because we've replaced the x in the function notation with a 4. And I'm going to use the graph on this one to find the value of the function. I want to know what output gets linked to this input of 4. So 4 on the x-axis is right here. So I'm going to have to move up to where the graph is, which is here. So since inputs are x's, domain are x's, that's the x value. And I have to go to the graph to show what y value is linked to it. Well, I'll go up to the graph and I'll look over at the y-axis and I see that 3 is linked to that particular input. So 3 is the output, 3 is the value of the function when x is 4. I do it again for when f is negative 1. Right? So I'll go to negative 1 on the x-axis, f of negative 1. I want to move to the graph, and I have to move up to get to the graph, and this graph is not perfectly straight. It should go all the way up here to 5. I look over to the y-axis to see what output goes with that x, and it's a 5, so the value of the function is a 5. F of 2 means I go to 2 on the x-axis, and now which way do I need to go to get to the graph? I can go up or I can go down. But remember, we talked about open circle means we do not include 2 as part of the domain for that part of the graph. A closed circle says that we do include 2 as the domain for that part of the graph. What that means for us in evaluating the function is that we need to move up to the closed circle. We always want to move to the closed circle and look over to the y-axis and find that f of 2 is 1. Okay? Now, f of negative 50. Here's a bit of an issue because negative 50 is not on the graph. It's not part of our graph. So, we need to move to f of negative 50, but we can't. So what we do is we try to find out which part of the graph negative 50 on the x-axis would be, and then just use that equation to evaluate it, right? Since negative 50 is definitely less than 2, we want to use this part, right? I want to take negative 50 and plug it in, I want to take negative 50 and plug it in for that x. And then I can just do some arithmetic to find the value of the function when x is negative 50. Negative 2 times negative 50 is 100. 100 plus 3 is 103. Okay, so that's how we use the function to evaluate for a given x. Okay, you have to figure out which part of the graph you're in and then plug that x value in for x in that equation. All right? All right, so now you try one. There's the piecewise function. Graph it up, and then try to find the values of f of 3, f of 0, f of 5, and f of negative 24. I think using the graph is easy enough. When you turn the video back on, I'm going to talk to you about using the function each time to find those values. Okay? But go ahead and try it. Stop the video. You can start it back up and see if you're right. Okay, let's walk you through this really quick. All right, so the inequality tells us that the x-axis, the domain, is going to be broken up into two parts. One part that's greater than 3, one part that's less than or equal to 3. So at 3 on the x-axis, we know our graph is going to change. So there's our dotted line to let us know that. Then we're going to graph in the greater than 3 part, which is over here. We're going to graph y equals x minus 2, because x's are greater than 3 this way. And in the less than 3 part, we're going to graph y equals negative 1/3 x minus 2. Okay? All right, so 1/3 x minus 2. Negative 2 is the y-intercept. The slope is, I'm sorry, not negative 1/3. I think in your notes it's positive 1/3. So let's make this positive 1/3. So we go up 1, right 3. Or we can go down 1, left 3, right? We can draw this whole line, but we know that we only want the less than part. So we erase this part. We look up at our function and realize that we want this graph when x is equal to 3, because x is less than or equal to 3. So that means we want a closed circle right there. Now we're going to graph x minus 2. So we start again on negative 2. On the y-axis is our y-intercept. And our slope is 1 over 1. So we go up 1, right 1, up 1, right 1, up 1, right 1. Keep going if you want. And then you can graph this line. But again, we only want this equation as long as x is greater than 3. So we don't want this part right here. Since it's just greater than, it's not equal to, we do not want to include 3 as the domain in this part of the graph. So we open circle there. Okay? Now, just using the function every time to evaluate. F of 3. That means if I plug 3 in for x, what value am I going to get out? Well, I have to know which equation I need to use first. And since 3 is equal to 3, I want to use this line right here. Because the 3, if I plug it in for x, will satisfy that inequality. So I take 1/3 times 3 minus 2. 1/3 of 3 is 1. 1 minus 2 is negative 1. So the value of the function at 3 is negative 1. F of 0. Since 0 is less than 3, I'm going to use the same equation again. 1/3 of 0 is 0. 0 minus 2 is negative 2. And then f of 5, 5 is greater than 3, so now I want to use the top line. So we go 5 minus 2, which is 3. F of negative 24, I can't use the graph, so we have to use the function. Negative 24 is less than 3, so that means that we're going to use the bottom equation. 1/3 of negative 24 is negative 8. Negative 8 minus 2 is negative 10, so the value of f of negative 24 is negative 10. Okay? And that's all using the function itself. You can always check that with the graph if you want. Just go to the x-axis at that particular number. So x is 3 would put you right here. And that means you have to go down to the closed circle, look over to the y-axis, and see that the value of f of 3 is negative 1. And that's what we got. Okay? And that's all there is to it. All right? Hopefully that makes sense. If not, again, get in and get some help as soon as you possibly can. The last thing I want to talk to you about is how to write the function from the graph. Okay? And it's not that difficult because every piecewise function has the same structure to it. And so if you have to write the function from the graph, we're going to start with the same structure every time. Every piecewise function has an f of x, and then this brace, and then every piecewise function has a line for each different part of the graph. So in this graph, we see that it exists in two parts. So I'm going to have two lines in this piecewise. Okay, two parts because we have a line here and a line here. So then, every piecewise function has a comma if, and then an x is less than and an x is greater than. Now the inequalities might change a little bit. But since there's two parts, I'm going to have used one part when x is less than some number. I'm going to have another part when x is greater than that same number. Okay? So that's what we're going to start with. Start with your template. Every time, write this down. Now all we have to do is fill in the different characteristics of this particular graph. The first thing I go to look for is the fact that the graph is changing, it's jumping at this place right here, which is 1 on the x-axis. That means that we're going to use one line when x is less than 1 and one line when x is greater than 1. So that means that in this inequality, we want to put a 1. That's where the break in the graph happens. The closed circle is attached to the less than side. So the less than inequality needs to have the equal sign. So less than or equal to 1. Now that we've established that, we want to go in and write the equations of these lines. That's the last part that we need. Okay, and in your notes this looks a little bit better. I'm going to clean mine up. We want to make sure this line goes through the origin. Okay, so for the less than graph, that's this side over here, the y-intercept is 0. And we want to put this in slope-intercept form. Y equals mx plus b. Right? We already have the y by itself, because again, remember f of x means y. It's the same thing, so that's already by itself. And so we're ready to just put the slope and the y-intercept in to create the equation of the line. The y-intercept is 0 for this line, so I'm going to put a plus 0 in here, but we know we don't need that, right? And then we need the slope. So to go from one point to another point in the graph, so if I go from this point to this point, I have to go up 1, right 1. Up 1, right 1 is a slope of 1, so I get 1x. At this point in our lives, we understand that multiplying by 1 doesn't change anything and adding 0 doesn't change anything, so we can get rid of those guys and just have x. Okay? And so we're done writing the equation of that line. Now we have to write the equation of this line. I don't see the y, it does not hit the y-axis, so I cannot determine the y-intercept yet. So what I do is I find the slope first. Now I want to go from that open circle to this point right here. And in order to do that, I have to go up 1, right 1. So again, the slope here is a 1. So I get 1x. Now, to find the y-intercept, I'm going to use the slope, just work my way backward, work it opposite way until I get to the y-axis. Instead of going up 1, right 1, I know I can go down 1, left 1, and there. I'm sitting on the y-axis. That's the y-intercept. So this becomes plus 2. Again, I don't need the 1 in front of the x because 1 times x is just x. And so there's the equation, x plus 2. And that's all there is to it. Hopefully that seems easier than what it looks. It looks pretty complicated. But we're just filling in a couple of different numbers. Okay?